So as said, my name is Mariano Martinez Peck. I work at Instantiations. I was hoping I could say something like, nice to be here in Raleigh. It was a long trip from Argentina, but obviously that didn't happen. So then I said, okay, I will start with an ice-breaking joke, but then I realized that everyone is muted, so I will be the only one laughing of my bad joke. So I won't do anything like that, so I will just start. Um, yeah, I would have loved to meet you all there, but that's what it is. So I will be talking about how to improve the debugging experience in the IoT area. So as you can imagine, this is aimed for developers, as we are in the IoT Developer Month. But I understand that the IoT area is really wide. There are so many aspects that it's impossible for everybody to be expert in all of those areas. So I imagine there is a very varied experience levels in the audience. So I will try to keep things at a higher level uh, as much as I can. Again, the time is limited in the session, so we will holding the Q&A until the end. But if you don't want to forget the question, just type it. So I will talk a little bit about who is instantiation and what do we do, and then I will go into how to get past of the IoT buzzwords that we hear all the time when we look for IoT projects. And then I will give some background about debugging, what it is, why it is needed, and so on. I will show how various languages approach debugging. And then I will give some cross-platform debugging demos. So in this case, I will be debugging an application that will be running on an ARM-based Linux machine, and I will debug that from an Intel-based Windows one. And that will be the demo. And the last thing is that we will have the Q&A at the end, as we already said. Okay, so who is instantiations? Here I would like to do it quickly as a brief recap, because Seth and Alexander already talked about this in the cheat compiler presentation, but just in case we have people that is joining just for this session. So we have been in business for over 30 years now, and while we were founded in 1988 in Portland, our headquarters is in Raleigh right now, in North Carolina. We hit our stride in the 90s with a focus on Smalltalk and Java solutions. And that's where we forged relationships with very large companies like IBM. During that time, we became a founding member of the CLIPS consortium, which later became the CLIPS Foundation we probably all know. And then due to the strong relationship we formed with IBM over the years, in 2005, we got into agreement to take care of the support and development of their Visual Edge Smalltalk, which is now named the Bas Platform. In 2010, Google acquired our best-in-class Java products, and so we could focus completely on the Bas Platform. And currently, we are working on continuous improvements for Bas, as well as expanding into new areas like IoT, edge computing, and other types of custom software development and consulting. And just to be clear, while we have expertise in Smalltalk and Java, which was our roots, the skills needed to build our platform and tools require significant expertise in other languages like assembly, C, C++, um, also languages like Python, Dart, Rust. They are all familiar to us as well if the need arise. So let's go to the Bas platform. Let's talk about it. I would just, even if we are going to talk about other languages today, I wanted to give you a quick recap for when the word BAST comes up. So BAST, it's an advanced software development platform with the first release originated in 1993, as I said, as a Visual Age for Smalltalk from IBM. And since then, we had at least one yearly release of our 2 million line code base. It runs natively on Windows and Linux with Intel-based architectures. And as Seth said, we are rolling an official release for ARM32 and ARM64 Linux, which is coming in the next month. And that is really nicely suited for edge devices and cloud-based servers like AWS or things like that. Bas is high-level scalable and really productive. This is mostly because of our improvements on the platform all over the years, but also because Bas is based on Smalltalk under the hood. For those that even heard about Smalltalk, it was one of the first object-oriented languages. It has pioneered many of the concepts that you see today in modern software development, like the concept of the IDE, the Integrated Development Environment, the MVC, the Model View Controller, refactoring tools, the graphical user interfaces, and so forth. There are many things that were invented together with Smalltalk. But that aside, it's still being used by Fortune 100 and 500 companies, numerous small and medium-sized businesses, as well as independent developers. It is used in different domains, finance, insurance, healthcare, simulations, and agriculture, automation, and just to name a few. We have a big variety of customers and domains. So just to relate things back to our session today, the Bas platform has a unique way of approaching debugging, which is not only suitable for traditional software development, but also for IoT. So let's see, for starters, let's take a look at the big IoT picture. So when most people hear about IoT, they hear all of those buzzwords relating to new capabilities, new frameworks, new technologies, new domains, new market verticals, and that's basically everything you hear. And if you just Google IoT, you will see this kind of thing with all the words. Here is just a small amount of them, and I don't want to say that these words are not important. In fact, most of the cases they are, but I think that when we are creating software, some different buzzwords also came to my mind. For example, error handling, fault tolerance, debugging, and many more. And as developers, we know these things are important too, even if they are not talked about as much in the mainstream. So let's switch our focus to the software side and specifically on debugging, which is why we are here in this session. So let's start with some background of debugging and some things to consider. First, I'm sure most of you have debugged something before, but for those that haven't, it's generally the process of finding and fixing software bugs from your code. Um, that said, let's start with a fact that I think we can all agree on, and is that bugs are inevitable. Even the best developers could introduce bugs. They are humans after all. So in some cases, the time devoted to testing may be reduced to allow more important features. Maybe this is dictated by project managers or whatever. Some bugs may be forced into production even when identified just to meet deadlines. You know, we are always running. We sell projects for yesterday, and that's it's a bad situation. So these scenarios might not occur to all of the project all of the time, but I think it happens enough to be worth mentioning. And then when we bring IoT into the mix, then things get even harder to debug because now we have multiple platforms. We could have multiple operation systems. So if you're doing IoT and you're at the microcontroller level, maybe you are not even running on an operation system. But if you're on a higher level IoT or edge computing, you are running probably on top on an operation system, and there could be a lot of them. So it's something to take care and brings complexities to debug. Same for hardware, you could have multiple types of hardware. You could have small devices that do not even have the power enough to debug an error or to report an error. You could have deploy your system or your software into thousands of devices. So it's not like you have a web server, I deploy it in a server, and then you just fix the server. No, you could have deployed this on thousands of devices that you need to fix if there is a bug. And then you can have connectivity issues that we know that is very common on IoT, and many more issues that I might not even be aware. You probably know better than me. Okay, then when you factor in cost and the fact that more bugs are getting pushed into production, you put yourself in a difficult and costly situation. And today, almost everything uses software, and software could have bugs and manifest them. So it's not costly just from a monetary standpoint, but it's also because of time, human safety, and many more examples that I don't want to say because I will concern people. So improving the process that perpetuates or increase the chances of having bugs, it's important, as well as, for example, allowing more time for testing. But that's a separate topic. It's more about project management, software methodology. So I don't want to get into there. But regardless of our process, we will still need to handle this. So how can the analysis and fixing of bugs be improved during both initial coding and in production? And we believe that a robust and efficient tools for debugging are essential. And BAST is a solution to consider on this front. But before we talk more about the Bas platform, I would like to review how other languages approach debugging and the common tools they use these days. So the goal here is not to directly compare language and draw conclusions about which one is better, because we know that the language choice is based upon many factors. And we will talk about that later. So that's not the goal here. And one small disclaimer I would like to make is that for this specific section is that our team expertise is quite diverse. So if there are questions beyond my knowledge during the Q&A, maybe my teammates may answer instead of me. So for example, as you can imagine, I am not expert in assembly debugging. So this is kind of the lower level that we will see. You will ask Alexander if you have questions here. So basically, when you are debugging assembly, you have each CPU instruction gets a mnemonic name. And since you are debugging at the instruction level, it's very easy to lose track of the overall application because you are really low. So it's really difficult to debug from that point of view. Then it's even more complicated because the different CPU architectures like Intel, ARM, RISC-V, etc., they use different mnemonics for the instructions. So you need to know all of them. So debugging is a really manual process because you need to go stepping from one instruction to the other. It's a real manual process. It's not like you can debug an expression or statement. You can inspect and modify CPU registers and memory allocations, so that's good. And the typical tool we use here is GDB. Now let's go to C and C++ debugging, which is a little bit of a higher language compared to assembly, but C is usually called the portable assembly. You can still modify memory, but now you can't modify the execution flow as you were able to do with assembly, for example. You can now debug at expressions level or statement levels. You can still inspect and modify memory and registers as you were able with assembly. Tools used are usually GCC, Clang, Microsoft Visual C++, and so on. For Java debugging, and we are now going a higher level language, and OOP, you will be running on top of a virtual machine to run your code. Java is a statically typed language. You can now run expressions and analyze that in a live context. So it's easier to understand from your application point of view what is going on. Of course, you can't modify memory because this is a managed language in which the virtual machine takes care of the memory. So you lose that ability, but of course you have now higher level of abstractions to debug. Typical tools are OpenJDK, OpenChain9, so on. Python, it's practically similar to Java. You run with interpreter. The main difference here is that it's a dynamically typed language, so that could yield a slightly better debugging experience, but the rest is the same. As for the Bas Platform, it's based on a virtual machine as well. It's a dynamic typed language, just as Python is, for example. You have the ability to run in expressions, so it's practically the same. But about our tools, I thought that it would be better to show than to tell. So now you would need to allow me for a second because I need to change my screen. And I will need to share my second screen. And no, sorry, that was not the screen to share. It should be this one. Okay, and now you should be seeing a Windows machine, I hope. What you are seeing here, it's our main IDE, our Bas Platform. This is called the transcript, which is basically our entry point to the IDE from which you can launch all the different tools. This area here, it's kind of the console, as it is known in other languages. And I will just launch one tool which is called the Script Manager, which allows me to store code as well as scripts. And luckily, I can also specify which language, because we support many language. So my notes, I like to keep my notes in Markdown. So, okay, now it's much better. So this is kind of the agenda for the live demo. So I will start by giving a quick overview into Smalltalk and IDE. As I already say, Bas is based on Smalltalk programming language. Smalltalk is pure object oriented. Everything is an object and everything happens via message send. I think this is the most important sentence, and you will see that in a minute. Everything is, your code runs on top of a virtual machine, like most object-oriented languages. I show you already the transcript, which is kind of our entry point in the IDE. And now let's run some hello world and some basic tooling as part of our language. So I just open a workspace. A workspace is just a little place where you can type and execute code. So let me do a transcript show hello world from IoT developer month. So this is the Smalltalk syntax. I will just execute this and you will see it got printed into the kind of the console standard out, whatever you call it. And this is the basic, most simple example. We have a class, and we are sending a message with this argument. We could also do the other typical basic example, 3 plus 4. So if I execute this and I inspect the results, this tool is called the inspector. This is very common in Smalltalk to inspect objects. So here I'm inspecting the number 7, but as you can see, 7 is an object and it's an instance of a small integer. So 7 is not a native type that you unbox and inbox or you have to cast. 7, it's an object, just like everything else. And for example, here in this expression, the plus is not an operator like in other languages. This is just a method. And if you look at the implementers of that method, you will see that that method plus is implemented in float, fraction, large integer, number, etc. So all we are doing here actually is send the message plus to the receiver 3 with the argument 4. So as I said, it all drills down to everything is an object and everything happens via message send. So you can browse the code. For example, I can, let's say I want to show the class object, which is the root of the hierarchy as in most languages. So this is the class browser where I can just browse the class and its methods. And then let me get back to my agenda, but I think that's it for the moment. Yes. Okay, what I wanted to show you now is the demo that I will be using. Here, this is a simple web application, which is a traffic light. It's something as simple as you click on the light and the lights get turned on and off. And as you can see, here it says CSI traffic light. CSI is because this web application, it's built on top of, or using actually the CSI web framework, which is a library to build complex and rich web application in a Smalltalk, and it's supported and shipped with Bas. You can see I am running in localhost. And if we came back to Bas, we can see here that we even have a built-in web server. So here you can see I have a local web server which is listening on that port 7777, and it's the guy that it's listening for the request that we are doing here. Now, the purpose of this demo was to show how to debug and handle errors. So this demo, if you click on the green light, you will get an error. So I just click, and if I go back to my developer environment, you can see that now a debugger comes up, and you can see the problem is in this method toggle green light, where it's trying to send this message, and the method doesn't exist in this class and it failed. So that's basically the error that we are gonna to debug. And in this case, this is a really simple error. Normally, when you are debugging something in production, what you are debugging, it's much harder than that. I mean, it would be ideal if the bugs would be as simple as that. But for the sake of the demo, I prefer to choose a really simple code that demonstrates a problem. Okay, so the other thing that I wanted to say is I have next to me, I have a Raspberry Pi 3. While we have experimented with a lot of boards, we have run on every Raspberry Pi from the 0 to Pi 4. We have run on Pine 64, Rock 64. We have run on Tensor. We have run on NVIDIA JSON to run TensorFlow and other machine learning experiments. So the Bas platform is probably working on every Linux that can run on ARM or ARM64. But for the demo, I will be using a Pi 3. And you can see here I have a console which I have already SSH into the Pi. So you can see, just to be sure, I am running Raspbian 9. So you can see I am running inside the Pi 3, which the host name is Mariano Pi 3, very original name. And I have also connected via SFTP. So here it's a total commander, which basically it's a dual panel. On the right hand, so here I have the directory where my development environment stores and read the files, like kind of my working directory on my Windows machine. And on the left side, I have already connected via SFTP into the Pi. So I am already in Mariano Pi, Home Pi, Instantiations, Seaside Traffic Light app, which is the same directory that I am already here in my console. So what we are going to do here is that I want to deploy this web application from my Intel-based Windows machine into the ARM-based Linux Raspberry Pi. So for that, Bas allows what is called cross development, and that's why it's XD, cross development. And it allows you to bootstrap Smalltalk images, which would be kind of a runtime from scratch for a specific target operation system and CPU architecture, and just for your own needs. In this case, the traffic light. So I have already kind of created this runtime beforehand because you know, time is limited. But what I wanted to say is that from that bootstrapped runtime, I have created these three runtimes that are the resulting process of that. So we can tailor down our bootstrapped environment that we created, and then the output is these runtimes, which in the small talk they are called images, and you can see these are 3 megabytes and a half, which is really small compared to, for example, the development environments. It's in my case it's 47 megabytes because I have plenty of things loaded. So you can see how we can decrease the typical development environment from 47 megabytes to 3 megabytes and a half. And this 3 megabytes and a half, it's running a whole web application system. So but you could get much smaller than that. If you saw Seth and Alexander's presentation on cheat compilers, you saw that he used a benchmarks runtime, which was around 500 kilobytes. So it's, I think it's really small when you take into account that we are on a high-level language and object-oriented. Okay, so what I will show now, basically, it's 3 different scenarios. That's for debugging that I will run on the Pi, and I will show you the differences between these 3 debugging abilities. But before getting there, let me explain you a little bit. So this directory that I have on the Pi, the Bas 9.2, here is where our virtual machine for ARM resides. And I also wanted to show the size of the virtual machine because I think it's interesting as well. So the virtual machine with the whole X integrated so that you can run headful applications on the Pi, it's about 1 megabyte and a half. But if you're running something headless, it's even 700K, the whole virtual machine. So again, I think it's pretty small for certain area of IoT. And again, consider that we are on a high-level language, very rich. I think we are doing a pretty good job. Okay, and the last bit that we need to understand the demo is this bash script that I will be running. These bash scripts are really simple. Everything I do is just cd into that directory. I export some variables that are needed for the virtual machine to run properly. And then this is the important line, and this is where I am calling our Bas virtual machine, and I am specifying which runtime I want to run. And in this case, I am passing the argument, which I call it stack dump. You will see the other bash scripts are the same, with the only difference is that I specify a different runtime. So we have 3 of them for the 3 scenarios that I will discuss. So hopefully this is clear, and I will start with the first scenario. I won't run it because time is limited, but I will just show the results. The first scenario is what is called I call it the stack trace. It's basically if you hit, let's say you click the green arrow, the green light, you get the exception. And what most programming languages do when they get an error is they log a text-based stack trace. Usually there is some header with some information about the virtual machine, how the runtime was started. And then below that, you usually have what is called the call stack, which is written, and then you can kind of look for what was the exception. So for example, if I look for toggle green lights, I can see this is where the exception happened. When the toggle green light method was executed, there was a does not understand kind of exception. And as you can see, for example, if I would like to get more information about this object, this particular instance of the seaside traffic light object, I don't know more than what it gets printed into the log. And this will ultimately depend on the print string or debug string or whatever the error handling uses to print or dump the objects into the text file. So here, this is all I got, and I can't get more information than this. Again, this example, it's simple, but in the reality, they are way more complicated. So let's jump to the second scenario, which it's the first one that brings, which I think that brings value, and it's what I call the stack dump. So now what I did is I started the same application, but now I started it on the Pi with that small 3 megabytes runtime. Now if we go back to our browser, I will now need to go into my Pi, which is the one serving this web application. And here you see again the traffic light demo, but now running on the Pi. And I click here, it works. And when you click on the green, you will notice that the server is shut down. And this is on purpose, just for the sake of the presentation. In a production environment, you would handle the exceptions and throw a nice banner explaining the user that there was an error. But for the sake of the presentation, I simplify this, and if there's an exception, the server is shut down. Now, if we go back to the console, we see, okay, there was an exception, seaside traffic light component does not understand tune all off. Dumping a stack file, seaside 00, SDF, finish it, okay. So now, if we go back to the Pi and we refresh this directory, we can see this file that was dumped just a minute ago, and I will copy this file from my Raspberry Pi into my local machine. So again, this could be 1,000 kilometers away. I could, this is a plain SFTP. I am just moving the file from the Pi to my machine. And what I can do here is I can now go into the runtime that I prepare for this scenario, and I could say open debugger, and of course the debugger would be empty at this point because there was no error yet. But what I can do is add a stack trace, and I can select from my local machine the file that was dumped by the Pi. And as you can see, I get a debugger which is populated with all of the call stack that happened on the Pi sometime in the past. And I can browse each frame of the stack. I get it's clear to everyone that just watching this debugger, it's way more friendly and useful than when you watch a stack like this. So I think that's an easy point to realize. But that's not all. I mean, we have something which I think is even more important, and it's the fact that we can inspect the objects that were involved in that execution. So here I am inspecting that seaside traffic light component, and I can inspect its instance variables. I can see, okay, this instance variable was false by that time, this one was true, and this one was false. I can inspect all of the objects at the different frames to see their state. So now I don't depend anymore of what was printed into the text file. Like, I don't care what it got printed here, because I have access to the object just here. I can inspect the object and get all the information I want. So this was what I call the stack dump, and that was the second scenario that I wanted to show. Now I will show the third one, which I will now start the remote debugger, as I call it. Okay, now I will go back to my browser, refresh this. And now, okay, we see the same traffic light working. And now let's see what happens when I click on the gray, or the green button, sorry. And I need to click yes here. And what happens is that I got a debugger on my development machine. This is my Windows. I am lively at this point in time. I am debugging what is happening on the Pi. And if you see, the server is not shut down, it's still waiting. So it's waiting for the HTTP response. And I have the debugger here next to me in my development environment. And I can do a lot of stuff. So for example, let's say I want to browse the class of this object. So I can just browse the class, and I get a regular class browser, just as we would do in the development scenario, where I can browse the class, I can browse all of the methods, and I can see what's the source of everything. But that's not all. We can even change the code. So for example, let's say we want to change the red light. So let's say, or the green. Let's change the green. Let's say that instead of being green, I want it to also be red, so that the first and the third lights should be red. Okay, I just save the method. That's the only thing I have to do, just save. That's all I needed to do. And we will see later if the change has any effect. Now, apart from being able to browse the code and to change the code from the class browser, I can also change the code on the fly from within the debugger. So for example, here, let's say that I realize that this was a typo, and this should have been, let's say, this, set tune all off. So what I can do here is I can save the method, and what happened here is that the new source was compiled, a new compiled method was generated, the frame was restarted. So if you can see, only this frame of the call stack was restarted. So I am back at the beginning of the frame. And now I can continue debugging. So for example, I can do over, and then I can get into, and I can continue debugging with the change that I have just did. And even more, and this is probably the last thing I will show, you can inspect the objects. And in this case, I am inspecting an object that is living on the Pi, and I can see the state obviously. This is the live state of the object. I can even send messages to that object. So for example, self, it's what would be this. For other languages, it represents this object. So I can send, for example, the message print a string, and I execute this, and I get a CSI traffic light component, which is the result of the message print string. But to make something cooler, you can see that on the call stack, I had already turned all the lights off. So what I will do is I will send the message set yellow light, and we'll say true. And I will execute this. Okay, so I executed this into the remote object. So this should have it should have turned on the yellow light as well. So I close this, and now I can resume if I want. So the server is still waiting, the browser is still waiting. So I will resume the session. And let's wait for a second. Maybe time it out. Maybe it took too long. Oh, or maybe I didn't save the change. Oh yeah, I forgot to make the change. Okay, so you can see how the change was affected. If I click now again here, I won't get an error because it has already been patched. But you could see how you can debug code on the fly and make changes, and this makes everything more productive. Okay, so now I will get back to my slides. So let me need to share back my other screen. Okay. Okay. So I guess you now you saw the demo, and I think it all comes down to efficiency. Bas is very efficient, basically because it allows you to apply changes on the fly without recompiling all of the code. It allows you to investigate production errors with a very rich post-mortem analysis, as we saw with the stack dump. It allows you remote debug and hot patching even deploy systems. And in general, it shortens the feedback loop during development. You are in the debugger and you change something and you just continue. It's really short feedback loop. When we talk about efficiency, we like to think about this as time, cost, customer relationship, software quality. So efficiency at the end of the day has a big impact. So just to wrap up before the Q&A, I think you will have a great development and debugging experience if you choose the Bas platform for your project. But again, we understand that many factors go into choosing your development language and tooling, like available libraries, performance and hardware needs, deadlines, the team expertise on the technologies, just to name a few. Although, regardless of the different technologies our customers have been used over the years, we have been there to help them solve the problems, and that's basically what we do. Okay, So that was it. Yeah, I would be happy to answer questions if someone has.
Thank you so much, Mariano. Great presentation. Very
Thank you.
interactive. I see that some of these questions were answered inline, but Mariano, curious to know what blogs, people, resources do you use, make use of to stay up to date on best practices around debugging strategies?
Let me put back my.
And I was going to jump in on this too, because we
Okay.
talked about in the background a little bit, so I'll give Mariano a break. So yeah, I thought this is a really great question because we sort of have this, I mean, this is something I practice. I think a lot of other folks on the team practice it where, you know, and this is independent of just debugging. I mean, one of the first things that we like to do when we try out new technologies are, you know, for example, when I go look at a new language, one of the first things I do is I go check out the source code for the software development kit, learn a little bit how the underlining either, you know, if it's compiled language, how that works, if it's a virtual machine, you know, how that's working. I check out their issues, see the things. The nice thing, I think, especially to answer the question specifically from the debugging context and giving our experience on the team, I think what's really cool is, you know, with Smalltalk, I mean, kind of as you just saw, I mean, that's really the target for a lot of languages. I mean, I've been trying out lately things like Flutter and looking at some of the hot reload that you can do and trying to get a sense of, you know, how fluid this experience becomes. I think the target at the end is something what like Smalltalk can do. And I think it's nice to have, you know, folks like who are on the team who can try and look at things from that perspective to try to get the other things to that. Because if you don't understand the Smalltalk, you know, kind of the live programming environment way of doing it, you might just be stuck forever in sort of that, you know, doing, you know, slight incremental improvements to sort of the same paradigm of how you've solved it yesterday. And so that's kind of what we do and kind of specialize in. I'll let, I mean, Mariano has his own processes, so I'll let him jump in next.
Oh yes, I guess it's similar to you. One of the things that we have been trying to do hard in all the recent years is that we try to keep up to date with the latest technologies and architectures. So, for example, if you see even our own blogs, we talk about things like Docker, and we provide example with Docker. We talk about, for example, continuous integration. So I mean, we try to pay attention to what is going on with the rest of the languages because I think again we have unique features, but other languages do cool stuff as well. So we don't believe that we are necessarily the best in every single area. So we like to keep up to date and grab ideas from another languages. So yeah, I guess it's not a particular place we look for, but it's just a general feeling that we try to get the best from other languages as well.
Thanks, Mariano. Thanks, Seth. Next question we have here. Sorry, they're coming in quick now, so scrolling back up. How heavy is the full stack trace debugging? I imagine the stack trace file size would be configurable, correct?
That's a good question. I don't recall if it's configurable or not out of the box, but I remember doing that myself, in which you kind of define a threshold because depending on your object graph, you could be actually dumping the whole image, just to say something extreme. But in general, from what we have seen, or our customers have seen in the experience, it's usually between 5 megabytes. In that example, it was about 4 or 5 megabytes. I have seen maybe some about 10 megabytes. But yeah, you should ideally have some threshold. Of course, we have a special handling for some objects. For example, if you have a reference to the object Smalltalk, which is the root of the dictionary, it will end up serializing everything. So we have a kind of specializations to avoid serializing the whole image. But having a threshold, if it's not there right now, I think it's a good idea. Something I'm not sure if I comment, but we also have this kind of grouping techniques. So for example, the remote debugging, if somehow the connection fails, it can fall back to a stack dumping. And if stack dumping fails for some reason, it can fall back to the typical log or a string-based stack trace. So that's neat because you can start with a richer, and if they fail, you fall back with the less powerful. So you can kind of combine them. So I hope that answers your question.
Thanks so much, Mariano. It definitely did. Chris said yes, thank you. The next question here, I have not kept up with vast remote capabilities. Are they included in Instantiation standard documents somewhere? And if so, where? And if not, when?
Yes, it is. I mean, parts of, yeah, it is. You can see it, there are actually two sections. One is about general debugging, where we comment about these abilities, both about the stack dump and the remote debugger. And then there is a section in which, in fact, this example that I showed today, this seaside traffic light, we even decided to ship it with the product in the last release as an example that is ready to go. So you have this example ready to go in the latest version, as well as the documentation for this particular example with all the exact details that you need to do to run it and to see it for yourself. So I think to answer your question, yes, it's documented and even shipped as an example in the latest release.
Thank you, Mariano. We have a couple more minutes. If anyone has any questions, please put those in the Q&A box. Up next, we have Chris Meyer representing Hardshare. I just want to say thank you again to the whole Instantiations team that's here with us today, Seth Berman, Alexander Mitten, Greg Schultz, and of course, Mariano Martinez Peck. Just great presentations, guys, really awesome. Thanks so much. And as a reminder, these will be posted to Riot's YouTube channel and shared on the Meetup page, so stay tuned for that. Thanks again, guys. I really appreciate you being here today.
Our pleasure.